I was about to say, for once my computer was behaving and the TV wasn't. Okay, let's get started. Our last lecture together, ladies and gentlemen. This is our... Oh, is it not working? Hold on. Hold on. Give me a sec. Wait. Oh, that's... Hold on. I know exactly why it's not working. Because that's the wrong slide. Try that one. That was an easy one. Of course, it would be the last day I'd do something like that. Okay. All right, everybody. So just a little bit on housekeeping. Just to make sure that we're all on the same page in terms of how the grade is computed in CE 312. I did this on Monday, but I'll do it again just to make sure that we're all sort of on the same page. So let's start off with attendance. So everything that's on attendance is up to date on Blackboard, obviously, except for today, right? Because we just took it. So I'll get the attendance grades uploaded today, and then your attendance grade will be locked in for CE 312. The project's graded. Project grade's locked in. Okay, homework. Everything's graded except for 3 assignments. Homework 9.1 is being graded. Homework 9.2, that was the homework that was due today. How did that go? I'm hoping that was a short assignment, because I didn't want the last one to be super long. And then there's the bonus assignment for the course eval. A couple things about the course eval. The university survey closes at midnight. Okay. If you haven't done your survey, please do so. Again, this is one of those classes I teach pretty regularly, so if there's any feedback you have about what I need to do to improve it for future students taking the course, I really do appreciate it. And then if you upload a screenshot that you did the survey, I don't want to see what you did. And again, you can say I'm a poopy head, but as long as you just do the survey, I will give you bonus points on top of your homework average. Right before class, I checked the numbers. 21 of you have done the survey, but only 19 of you have uploaded proof. So for those 2 of you that did the survey but didn't upload the proof, you are throwing away homework points. Please, take free points. The university survey closes at midnight, but I'll keep the Blackboard upload. So in case you do the survey but you forget to upload, I'll keep that open until Monday, and I'll mention it again right before the final exam. Does that sound good? And everybody's got their at-home game spreadsheet, so you all can play the at-home game and figure out what you need to get on the final to get whatever grade in the class. Okay, does that sound good? Everybody get the code? Okay. Let's talk about the final. Okay, so a couple things about the final, and I want to make a point about something that I did. So the one thing I've decided to do, I am not going to add topics on the final, but I have decided to add another problem, and I'm going to tell you why. My main reason is not to penalize you. It's actually the exact opposite. It's meant to help you. So the way that this final works, one of the biggest topics on the final is influence lines, right? That's like the biggest thing we talked about since the second exam. And the thing about influence lines is they're very difficult to assign partial credit if you get it wrong, because you know how, you all remember influence lines. You sort of just draw it, right? And it's either right or it's wrong. And so what I don't want to do is have some really big problem on the exam that you either get right or wrong, because it leaves very little room for partial credit. But if I add another problem or add something else onto the exam, then that softens the blow on influence lines. And so that's what I've decided to do. It's still not going to be a time-sensitive exam, and I think when you see this this additional problem that I've added, and I'll admit I even kind of have a hard time saying this additional problem's a problem, because it's much more conceptual than it is computational. You'll see what I mean. It's definitely not anything to stress about it. It's a pretty straightforward problem. The one thing I do want to mention, though, in terms of your preparation, is that you are still allowed a formula sheet, but you don't need to worry about these. I'm going to give you these on the final, okay? So I'll have one for everybody in here, so everybody will have a copy of these, and I'm gonna leave these here in case anybody wants to grab one. Afterwards, I'm gonna get rid of them, but these are on Blackboard as well. So I don't want you to waste time on your formula sheet putting that stuff on there because I'm gonna give you that, okay? Does that sound good? Okay. All right, so again, the big thing that I say about the formula sheet, I just want you to make it. You know, take some time and make it. Don't just copy and paste slides. Again, I think that will more or less injure you in your preparation for the final, because I think by making the formula sheet, you are studying. So I want to see you do well. Okay, let's talk about what's on the final. Okay, and what's on the final is basically everything that we talked about since exam 2. And so we've basically talked about 3 things in this class since then. We've talked about influence lines, which is a big topic on the exam. But then we've talked about masthead, and we've talked about matrix analysis. You are not going to need to do a masthead analysis on the exam. So this isn't going to be like bring your laptop and do a masthead analysis. It's not that. I might ask you questions about masthead, but I'm not going to make you break out your computer and start performing structural analysis together. Does that make sense? So no masthead analyses. This is all just pencil and paper, okay? All right, so the topics. Okay, so influence lines. Make sure that you can draw an influence line. And so by drawing an influence line, what did we do in here? We drew influence lines for vertical support reactions. We drew influence lines for shears and moments at a given point. And we drew influence lines for fixed supports in terms of reactions and internal response. We also determined, be able to use those influence lines to determine worst case responses. Specifically, worst case responses due to concentrated loads and distributed loads. And also we want to be able to, the real goal is to take those influence lines and determine worst case maximum responses, right? So remember the way that we did that is we said that dead loads, you know, if I give you a dead load of 2 kips per foot, that's everywhere on the beam. But if I give you a live load of 1 kip per foot, you just put that live load wherever you need to put it to generate the worst case response. And so that's what we mean when we say envelope responses. For the masthead stuff, I want you to have a general understanding of the matrix stiffness analysis process. But for the masthead stuff, I want you to be able to understand the basics of masthead operation. So what does it mean to create your geometry? What does it mean to apply properties? What does it mean to apply conditions? And by conditions in masthead, we're talking about fixities and loads, right? What does it mean to perform the analysis, and what does it mean to perform the results? Like what are, you know, like nodal displacements, like, you know, stuff like if I said I wanted to, like, here's a conceptual question for you. If I said, give me a plot of the deflected shape at a magnification scale of 40, what does the 40 mean? It means that you're taking the actual displacements and multiplying them by 40 so that you can actually see what's going on, right? Because if you have a 30-foot long beam and it deflects 0.2 inches, you can't see that, right? So you artificially magnify the displacement so you can actually see what's going on. That's the kind of stuff I'm talking about in terms of conceptual questions. For the matrix analysis itself, I want you to understand the process for bars and trusses, okay? Those are the 2 systems that we talked about in here. I want you to be able, ignore that bullet because that was a bullet for the project. So yeah, ignore that bullet, that was for the project. I took this presentation from the project and then just sort of added it, so ignore that. And then perform the associated matrix computations. So what I said before the, I think I said this on Wednesday before this review, was I am not going to make you do a full-blown matrix analysis problem start to finish on the exam. There's no way I'm going to be able to do, make you do that and expect that you can do that in 2 hours. That's ridiculous. But I might say, here's here's an example. I might go, here's a stiffness matrix, reduce it for boundary conditions. You know what I mean? So if I give you an 8x8 stiffness matrix and I say, okay, this, and this are restrained, what does the stiffness matrix look like afterwards? You would just knock out the rows and columns and there's your stiffness matrix. So I might give you something like that. You know, make sure that you understand how to assemble, that make sure that you understand the general process. So I might give you stuff like that, but what I'm not going to do is give you a full-blown problem. Again, I meant what I said in terms of the rule of 3. There should not be any time constraints on this exam. You have 2 hours to do this exam. You should have more than enough time to complete the test. In terms of what's left in this slideshow, everything else is just sort of relevant stuff from the past few lectures. So for example, influence lines first. So influence lines, remember, for drawing for reactions, we have a few rules that we can use. So remember, influence lines are linear for determinate structures. This is a determinate structure. How do we know it's a determinate structure? Let's pop quiz that one. How do we know that's a determinate structure? Y'all remember this? How about this? How about we have 4 reactions, right? We have 1 hinge, right? So it's determinate, remember that? If you have a determinate structure, the influence lines are lines, okay? They are linear structures, okay? The reason why, I mean, there's one reason that can be stated about 50 different ways, but the way I like to describe it is if I remove one of those supports, the structure becomes unstable, and unstable structures don't like flex into form. They just kinematically, boom, they just go. So, you know, for example, if I remove the roller at C and lift point C up, it doesn't flex or bend, it just lifts up like this, okay? And speaking of, that's how you construct the influence lines. You remove from the structure the ability to respond at the point of interest. You move that point through a unit displacement, whatever the structure looks like afterwards, that's the influence line. So when you're drawing influence lines for reactions, they equal 1 at the reaction of interest and 0 at all other reactions. So 1, 0, 0, 0, 1, 0, 0, 0, 1. Linear everywhere else, and whenever you have an internal hinge, it just changes the direction of the line. So we have an internal hinge between B and C, so for every influence line you can see like a change in slope, change in slope, change in slope. For shears and moments, we put either a shear release or a moment release at the point in question. And so for moments, what we do is we basically just pick that point up, and we pick it up some height such that this slope plus this slope equals 1. I think moment influence lines are actually easier to derive. For shears, we mark the left side tends down, the right side tends up, and then the idea is that these two lines have the same slope, and the sum of that displacement is 1, and so you just have to solve that out. Again, they're linear, and again, hinges still serve to change the slope of the line. For matrix analysis, okay, so for matrix analysis, the way that masthand works and the way that this works, okay, so the first thing that we do is pre-processing. So this past week, we haven't actually had to do any pre-processing because I give you a homework problem and the pre-processing is already done, right? You know what the geometry of the problem is. You know what the loading of the problem is. You know what the stiffness of the problem is. Like homework 9-1, I gave you all that. Whereas in masthand, you had to go into masthand and actually do that. Create the nodes, create the elements, create the materials, create the sections and all that. That process is called pre-processing. Now in masthand, what happens is you click a little button, masthand does all this hullabaloo, all this stuff down here inside masthand, and it just gives you the answer, okay? So in masthand, pre-processing is creating the model, and post-processing is reporting and understanding the final answer. So post-processing would be like plotting the shear diagram, plotting the deflected shape, recording all the responses and things like that. But we now know after this week and a little bit of time before break, we now know what's happening when you click that little analyze button or you click that solve button. Masthand is sort of operating in a 4-part sequence. And I'm not like talking specifically about the structured code inside masthand, but I'm saying all matrix analysis solvers tend to operate like this. The first thing it's going to do is it's going to write the spring matrix or the K matrix for the whole system. And so the way that it does that is it writes a stiffness matrix for each member, and then it assembles it. In the case of a truss, we have to take that stiffness matrix and map it to global coordinates, and we know how to do that now. We take T transpose times T, K prime times T before we assemble. So we assemble the K matrix and the F vector. Once we do that, we knock out the rows and columns of K and F based on the boundary conditions, and then we can solve for the displacements. And once we get the displacements, we just say, okay, let's do F equals K delta to get the reactions, and let's take each of the displacements and form a little displacement vector for each element, and F equals K delta for each element to, there we go. And that's pretty much all there is to it. In terms of matrix analysis, this slide is probably common to both Mastan and this, and that is that, so first off, our terminology, we know that we're using the terms joint and node interchangeably, and we are using the terms member and element interchangeably. For units, matrix analysis doesn't care about your unit system. So what that means is that whenever you're starting the problem, everything needs to be in a consistent unit system before it starts going through the flowchart, okay? And so in USCS units, I typically recommend that your forces need to be in kips and your displacements or your lengths need to be in inches, okay? For the sign convention, because we're doing this in a matrix type procedure, we sort of have to adopt something consistent and just go with it. So we're going to say everything going to the right is positive, so forces and displacements to the right are positive. Anything going upward are positive. The rotations, that doesn't really matter for bars and trusses, so we can ignore that. But axial forces in truss elements, we've been saying tensile forces are positive. And this one comes into play because whenever we get to the very end of the bar problem or the very end of the truss problem, we just look at the second number of the truss element, and if it's positive, we say it's tension. If it's negative, we say it's compression. And if we said compressive forces are positive, we would either flip that sign convention or maybe look at the other number. Here's Mastan 2. Here's the interface. Again, basically the way Mastan works, we start here, work our way over, and the model's done, right? And that's how we did it in class. That's how basically Mastan works. And I use Mastan as my reference, but really any structural analysis or finite element analysis package works this way. Whether you're doing something as simple as a basic truss problem or modeling the space shuttle, it's all kind of the same way. You define the geometry, define the properties, define the loads and conditions, analyze it, and post-process the results. Here's some guidance on nodes and elements. Nodes are, so like what is the deal with nodes and elements if you want a definition? So nodes are where the structure will directly compute deformations. And what happens in matrix analysis is that everywhere else you interpolate the displacements. And so where do you put nodes? Put them at the supports, put them at the hinges, put them at the truss joints, put them at point load locations, although that's not 100% necessary, but I'm getting down the weeds of matrix analysis land. It is in Mastan. And any other point of interest. Elements, the way matrix analysis works is a model's broken down into discrete solution regions called elements. And when we start getting into more advanced problems, the number of elements affects your final answer. And the way I like to explain that is if you had like a function in a math class that like looks like this, right? And we wanted to idealize that with a series of straight line segments. Well, if all we did is use one straight line segment, that would be a very bad approximation. But if we used, let's say, 3, suddenly the idealization gets better, right? And so what I'm saying is if the problem is nonlinear, the number of elements matters. But everything we've done in this class is linear. So how do you approximate a linear region? Just use one element, right? So we would never need to write a truss element and put multiple elements per member. We wouldn't need to do that. In Mastan and in matrix analysis, whenever you're defining the geometry, really the only thing that matters is you have a consistent origin. So like if you had a beam that was 100 inches long, this could be 0, 0 and 100, 0. This could be 80, 0 and 180, 0. This could be negative 150, 25 and negative 50, 25. Because now you know, I mean, what is the solve we're going to do? It's going to take the change in x and the change in y to start computing sines and cosines and lengths. And so it's not really going to matter. You just need a consistent origin and you need consistent units. The only other stuff that I could put in this slideshow, I chose not to because it's on these matrix analysis handouts, like the process for bars and the process for trusses, and so I thought it would be repetitive. That's the exam. So I'm going to shut up now for a little bit and turn it over to you for questions. Nobody has questions? Am I getting off easy? I could bring up some MATLAB code. You don't want me to bring up any MATLAB code? Oh.
You're just such a good teacher. You just don't have any questions.
Is it that, or is it just, as we were talking about before class, well, let me ask it this way. How many people in here are just about done this semester? Just, we're here, we're just done, ready to go home, realizing that the best invention ever is the Snuggie, because you can just sit on your couch and just, you know, break out the Nintendo Switch and play Zelda for a month. What's that?
Those are your plans? It's awful specific.
So here's how I'll answer that. Those are my plans, but it's not going to happen. Just tell you that. That's just, I can tell. That's not going to happen. I put Zelda in my lecture slides. What do you think? Of course, he's my plan. I put Mario and Zelda. In statics, I used Yoshi for my friction problem.
You did?
We should have had more references in this class or something like that.
I guess I should.
I don't know when you could
Use the lightsaber. Use the samurai sword.
Maybe I need to make like all of my structural analysis problems reference like pop culture, like every one of them.
Yeah.
Like SpongeBob is moving a load along this beam where SpongeBob needs to put the load to generate maximum response.
Yeah. If only you had like a big reminder you could hang on.
You all have way too much time on your hands.
I'm gonna have a lot of time on my hands walking next week.
Yeah.
Maybe some days.
Maybe we should. Yes.
We will have a question about design tandem and
That's a good question. So the question is.
design lane.
So the question was, will there be a question about the AASHTO loading, design truck, design tandem, design lane? The answer is possibly, but let me qualify that answer. The difference between what we did on homework 8.4 and 8.5. So on homework 8.4, I said, here's an influence line, determine maximum response for a load. And then on homework 8.5, I said, okay, now do the same thing but for AASHTO loads. So the process between homework 8.4 and 8.5 was exactly the same. Really what probably made homework 8.5 just take so long is that the loads are intricate, they're complicated. You have these, you know, like the tandem has 2 axles, the truck has 3 axles, and you just sort of do the same thing over and over again. So I'll answer the question this way. The answer is possibly, okay? But what I can tell you won't happen on the exam is doing the same thing over and over and over and over again. Because at that point, it stops becoming an exercise in your understanding of structural analysis, and then it just becomes how fast can you hit buttons in the calculator. So I'll give you some specifics. If you go to the example problem that we did in class for the truck, the lane, and the tandem, right? We did we had 12 different answers to that problem, right? Because we had, for the truck, for each component, the truck, the lane, and the tandem, we had a worst case positive shear, a worst case negative shear, a worst case positive moment, a worst case negative moment. I might ask you one of them. You see what I mean? But at that point, asking any more would just be the same thing over and over again. I might ask you one, I might ask you two, I'm not asking any more than that. So, to fully answer your question, is it fair game? Yeah, it's fair game, but it won't be time sensitive.
Are you gonna have any indeterminate structures for influence lines?
Indeterminate structures for influence lines, not ones you have to do. I might ask you a conceptual question about it, but no, you're not going to have to do anything. And in all honesty, if we were teaching an advanced structural analysis class, like I might do something like that on a homework, but I wouldn't do that on an exam either. I might ask you some questions about it conceptually. That's about it. Having you do a quantitative influence line for an indeterminate structure on an exam doesn't seem like a valuable use of anybody's time. Whether you were in grad school, undergrad, it wouldn't matter. So that's just my opinion. So.
What do you think the hardest problem is going to be?
I'm going to answer it this way. I'll give you actually a more direct answer than you were probably expecting. I think of the 3 exams, I personally think this one's the easiest. I mean that. I'll be blunt. I think the hardest problem would probably be the influence line one. And the reason I say that is because I just think matrix analysis is easy. Like, I think what makes matrix analysis quote unquote difficult is that it's just long. But I'm telling you, I'm not giving you a test that's going to take 7 hours to complete, and I'm only giving you 2 hours to take it. So if I take the time constraint out of a matrix analysis problem, it suddenly becomes a cakewalk. You see what I mean? So that's my answer. I think that the influence line problem will probably be the most challenging. But I say that with the context, I think of the 3 exams we have in this class, this one's the easiest.
Also, are we going to have to multiply a matrix by hand?
No. With the caveat, all right, hold on. At most a 2x2, nothing more.
Will we have to know how to transpose by hand? Transpose a matrix?
I think you should know how to transpose by hand, but transposing by hand is easy. Just yeah, you will not have to invert you will not have to invert a matrix by hand. You will not have to do that. And I'm being cagey with my words because, like, if it was a transformation matrix, the inverse is the transpose. So. Yeah, nothing. There will be nothing on this exam that you can't solve with the Casio FX115 ES Plus or similar scientific calculator. Nothing substantially challenging. So. Anything else? Has it been a fun semester, hopefully? That I get my evals. This class was straight trash, Dr. Mike. Nah. I'll say this on a closing note. For those of you that are taking steel, like a lot of you are, right? Steel is different than this class. This class felt, I'm sure at times, very theoretical, very solve for X type class, matrix math and derivatives. Steel's not like that at all. It is very applied. When you get an answer at the end of the day in steel, you really do, you get it. There is, the answer is use a connection of A325 3/4 inch diameter bolts that are spaced 3 inch on center. You use 12 of them in a 4x3 pattern with an edge distance of 1.5 inches. Like, you're like, okay, like I see that. I can build that, Whereas with here, you get like an influence line plot, and you're like, okay, how do I take that influence line and go build a bridge? You see what I mean? There's an abstractness to structural analysis that does not exist next semester, I would say. Next semester, you really can sink your teeth into the stuff, which makes it, I I've had students that say that like they enjoyed this class, but they didn't enjoy it as much as like a class like concrete or a class like steel because it's much more down to earth, and I can appreciate that. So, but I love teaching steel. So, I will have more information about the manual as it comes, but there is no textbook for steel design. You have to get the manual, but there's no textbook. So, and the manual's like I think 125. But if you have a friend that has a manual from a previous year and you want to borrow it, that's fine. It just has to be gold. And if you don't know what I'm talking about, the steel manual gets published it gets revised every few years. And so this current edition is gold, okay? The edition before that had like a teal color. The edition before that was sort of like your shirt, like a maroon, like a burgundy type thing. And so if you came in with like a teal manual or a burgundy manual, it wouldn't work because there's enough that's changed in the manual that it'd make your homework off. But if you bring in a gold manual and you want to borrow it, that's fine too. It's just got to be gold. They said it was the gold standard when they chose the color. I was like, I see what you did there. Funny. Again, I'm an engineer. I embrace the fact that I'm a little bit of a dork. It's okay. All right. Any questions? Anything else? Anything else about the final? Does everybody feel comfortable about it? Is there anything about the final that's making you nervous or worrying you? Does everybody want 17 minutes of their life back? Well, guys, it's been a blast. I love teaching this class, and I hope to see you all again in steel design next semester. If I don't have you in steel next semester, hopefully I'll have you again. It's been a blast. I'm the associate dean, so I imagine if you need anything, you can come see me. Y'all know where I'm at. But we'll see everybody.
Dr. Mike, as the associate dean, I already rolled up like 8 on the walls.